Membranes are selectively permeable barriers, and we use them for filtering things from gases and liquids. So for example, we might want to filter particles out of a liquid, and we use them to filter sometimes molecules out of liquids. And in gases, we use them to separate one type of gas from another. Applications of membranes are very broad. So membranes are used, for example, in the production of fresh water from seawater by separating salt from the water. Membranes can be used in kidney dialysis when you're trying to filter the blood, and membranes can also be used to separate oxygen and nitrogen and to provide gases for medical uses. One of the issues with using membranes is always how much flow you can get per area of membrane, and we call this the flux of the membrane. So the lower the flux of the membrane, the more membrane area you need to provide. And the more area you need to provide, the more costly it is to use membranes. And whilst membranes generally use less energy than most other separation processes, that cost of using the membranes means that we can't always use them at a very large scale, because as the scale gets bigger, we need to provide more and more and more membranes. So a key challenge is how we go about making membranes with higher permeance, which means for each area of membrane, we get more gas or liquid passing through that membrane. We've made membranes which are very thin, so they're 8 nanometers in thickness. And if you want to get a feel for what that means, if you were to take these membranes and stack 10,000 of them together, the thickness of that stack of 10,000 of our membranes would be roughly the same as the diameter of a human hair. And we've also managed to manipulate the morphology of the membranes, which means that we can make the membranes either smooth, completely smooth surface, or we can make them with a very crumpled surface. When we make them with a crumpled surface, it turns out that they have a much higher surface area for each area of membrane, which means we get a much higher permeance. We were very surprised with that, because we thought when we made the membranes with the crumpled surface that when we applied pressure to them, that pressure would flatten out the crumpled bits and we wouldn't get any flow. But it turns out they're also very strong, and so that while the membrane has corrugations and is very crumpled, it doesn't collapse under pressure. We can apply pressures of up to 50 bar to these membranes without seeing any change in their structure. And if you want to think about that, that's the equivalent of being something like 600 meters under the surface of the sea. That's the weight of water you would have on you is about what you would feel if you're one of our membranes. And under that kind of pressure, even though they have a very crumpled structure, they do not change that structure. The most likely use of these membranes is going to be in industries where they are processing organic liquids. So where they're using a technology, probably evaporation, to concentrate up an organic liquid or to separate molecules in organic liquid. So for example, you could imagine separating out molecules that are present in large volumes of organic solvents in the petrochemical industry, polymers from solvents. You could imagine separating crude oil. You could, instead of using distillation columns, or as well as using distillation columns, you could use membranes to make those processes more efficient. Or if you're making a fine chemical molecule, for example in the semiconductor industry, and you want to purify a solvent, you could purify it through this membrane instead of having to evaporate that solvent and condense it. Or in a pharmaceutical industry, when you want to concentrate a drug molecule that's present in a solvent, you could use these membranes to do that.